This is a lesson on scientific process and number basics. Scientific process is a generalized process. It's not in any real set order, but in general, you do a process of collecting data, which leads to a hypothesis, which then leads to an experiment to test that hypothesis. Once you do your experiment, you cycle back, collect more data, figure out the hypothesis, and this process goes round and round and round, using different scientists in different areas in different labs, and eventually you'll come up with something called a theory. That theory is highly probable, but not a certainty. That theory is used to make a prediction. That prediction leads to another experiment, which you might need to modify the theory which would lead to a new prediction, and then that goes around and around and around. The concepts is pretty much the same. This is dealing with one specific situation. The theory is more generalized. The difference between a law and a theory, what a law does is it summarizes the observations, like, for instance, a law of gravity, things will fall to the center of a mass, such as the Earth. The theory has an explanation on top of that. So it will summarize, and it will also explain. The mass will fall towards the center of another mass, such as the Earth, because there's a mutual force of attraction between the two. So that's the difference between those. Units of measurements. When we do experiments, we do measurements. That's the key thing that separates modern science from ancient science. The units of measurements, SI units, System International. There are seven defined or fundamental units. Meter for distance, time, or second for time. Kilogram for mass. Mole for quantity. Candela for brightness. Amps for electrical charge. And Kelvin for temperature. These are the 7 SI units. These are fundamental units. There are derived units. Derived units are made up of more than these, usually based on a formula. For area is length times width. Length and width are both meters, so that's meters squared. So a derived unit would be meters squared. For area, speed, meters per second. Take the meters divided by the seconds, and these are also formulas. Distance divided by time is velocity. So these are derived from an equation, and instead of putting numbers in, you put the labels in of the things you're measuring and plug them in. That's your derived unit. There are also prefixes. The main prefixes that we would use in a high school science class would be kilogram, kilo, for 1,000, deci for a tenth, kilo is 1,000. Centi is 100th, and milli is 1,000th. There are more than that. Things that we might be using later on in science is nano, like a nanometer, which is 1 times 10 to the negative 10th. That's frequently used. And micro is occasionally used, 1 times 10 to the negative 6th. So those are 2 additional ones that we use in chemistry. Measurements, again, when you make a measurement, it's a human endeavor. Therefore, the scales and the people measuring the scales are there's a limit on how well we can do things. So there's the uncertainty. When you make a measurement, the last digit is an estimate. You're reading in between the scales. If this is 1 and this is 2 and the line goes here, you estimate. You can't say it's 1, you can't say it's 2 because it's somewhere in between there. Call it 1.7 or so. Now somebody else might call it 1.8. Nobody will probably call it 1.1. If it was dead on the line, if it was dead on the 2, you call it 2.0. If the scale goes up by ones, the estimated digit is the tenths. If the scale goes up by thousandths, then the estimated digit is the 10,000ths. Sometimes, once in a great while, they'll show uncertainty 3.65 plus or minus 0.01. This is especially true if it's not going up by a tenth. If you're going up by 2/10 or something like that, then the last digit isn't off by 1, but it could be off by 2. Accuracy and precision. Accuracy means you are close to reality. What the accepted value is, what the true value is accuracy. Precision is reproducible. The values are bunched up. You can have a very precise instrument that's not calibrated correctly, so its accuracy is not well. A lot of these depends upon the quality of the machine and how well you do your job of measuring and recording instrumentation. Significant figures, significant figures, sometimes significant digits. You use the Atlantic-Pacific rule. Here's the Atlantic Ocean. Here's the Pacific Ocean. If the decimal point is absent, then you start from the right-hand side. If the decimal point is present, then you start on the left-hand side. So the decimal point is absent, so you start on the right-hand side, ignore zeros. They're placeholding zeros. They're only there to show you that it's 3,700, not 37 or 37 million. So coming in here, you ignore zeros, 1, 2. So there's only 2 significant digits here. If it was that, there's a decimal point present, so you start from the left, and you start counting numbers after the very first non-zero number. So then in this case, it would be 4. So that decimal point there does mean something, and when we do homework, make sure you know how you do that. Now, if you wanted to show 3,700 with 3 significant digits, well, if you write it this way, you only have 2. If you write it this way with a decimal point, that's 4. How do you show 3? The easy way is scientific notation. 3.70 times 10 to the third. Anything in front of the times 10 to the power is going to be the significant digit. So this would be 3.70, that's 3 significant digits. Scientific notation is very helpful when you do this. Define values. If you're given a value for like value of the mole is 6.02, use an infinite number if it's defined. If you have a whole number of things, like 1 atom, 2 atoms, 3 atoms, that would be an infinite number. So you're not limited on those. So if they give you a value, or if it's a whole number, or a number that you know is going to be an even number, like 2.5, 2.5, it's going to be 2.5. You can't have less, you can't have more. So if it's exactly that, you do that. Usually the significant figures only are involved with the measurements that are taken. So you're only concerned with the numbers where a measurement was taken and put into an equation. 3.14 r squared. This is pi. You didn't measure pi. You were given pi. If you go to a book, you can get a bigger value or worse value of pi if you want. R is what you measured. R is the value that you're going to restrict your significant digits to when you calculate them. When you multiply and divide significant figures, you just do all the calculations. Do all calculations first. Then, at the end, you round to the significant digits. Do not round every step. Keep in your calculator, keep going, keep going, keep going. When you get done, go ahead and do that. With addition, subtraction, my theory is go ahead and add them all up. There are different ways of doing this, but most of the time in chemistry we're not going to change instruments. If we're going to use the type of scale for grams, we're going to use the same type of scale for grams every time. Technically, I'll show you, you're not going to be tested on it, 3.5 and 200.17. If you were to add, you would add all these up and round to the number that has the least accurate number. This is to the ones, tenths, hundredths. Ones is less, so you round off to the ones digit. So your answer would be 2.18. Again, if we're using scales, we're not going to be bouncing around from one type of scale to another. So most of the time in science, in chemistry class, you're going to have 14.00, 5.50, 200.17. You're going to have the same scale. These are grams. Your digital scale is going to read out to that number, and you don't have to worry about it. That ends this lesson.